how much of that content do you think we have currently covered or we're covering right now? How much of all of that content, it was 10-minute video, how much of that is stuff that we're currently doing in this module? Maybe 90 seconds, right? Maybe 90 seconds worth. So why would I show all of that to you? What's coming up, right? And why it's important for you to be able to understand this stuff, because like with a lot of things, as you're learning it for the first time, as you're encountering it for the first time, it seems difficult, but it's really foundational for the next step. There's more that's coming. And that's why don't treat each piece of information as that's the terminal objective, the terminus. So I get there, I'm going to understand that. Once I got that done, I move on to something else that's completely disconnected. That's why in this module I've chosen to go ahead and take a few extra days on this material, is because even at the level we're at teaching right now, though maybe 90 seconds of that whole video was actually what we're in right now for this module, I would hope that there's at least one person in this room that understood probably 75% of what was up on the screen, right? Because probably 75% of what was on that video is stuff we're going to cover through the course of this year. So in this course, most of that material, and maybe not exactly the way it was explained up there, but when he started talking about the bent molecule of water, the double bonds, triple bonds, all those kind of things, you're going to be into that a lot quicker than you realize. And what he said is going to make a lot more sense. Matter of fact, it might have been insightful for us to watch a video like this and then watch the same thing when we're done with the course. You go, you know what, I can actually hang with that. I actually understand. I couldn't maybe come up with it on my own, but I understood what he was trying to say. And that might be a victory for some of that content. But probably 50 to 60% of that video, by the end of this course, you're going to be like, yeah, everybody knows that. But we can't get there until we understand, right now, electron configurations. So let's go ahead. Again, because we are kind of stretching out these last few days, I hope you don't view the last few days stretching it out, meaning you've got less to do in preparation for the exam, but because it's a difficult module, or at least it's a fundamental module that you have to understand, I hope you've taken advantage of the slower pace to actually do maybe more of the reading than you normally would do, maybe work some of the problems a little earlier than you would have if we'd done this module in 2 weeks, okay, because we're taking and stretching it out to 3. So let's go ahead into module 3. I want to make sure I cover the notes that are in the book, and then we'll go back to some just general learning. And as I've done, especially in a module like this where I tend to slow down and go slow, I like to start with a repeat of what we've done. Again, just kind of reaffirming that you need to know this content, you need to know how to work these things. And when we're doing electron configurations, remember, electron configuration diagram is just a shorthand of describing the address or the location of all of the electrons that are present within that ground state atom, okay, the ground state atom. Now, when I talk about ground state, it's a little bit different than before when I would say, okay, we have a certain atomic number, and we can take the atomic number and the atomic mass, we can calculate how many protons, how many neutrons, and then say the number of electrons is equal to the number of protons because it is in a neutral atom. Neutral meaning it's not an ion, right? So the number of electrons equals the number of protons. If we had more electrons, it would be a negative charged atom. If we had less electrons, it would be positively charged. But because we have the same number of electrons as protons, it's neutrally charged. They balance each other out. When I talk about electron configurations and I say that the configuration is for the atom in its ground state, what I mean by that is not that we have more or less electrons, which would make it an ion, but in its ground state, the electrons are in their lowest energy level possible. If it's not in its ground state, it would be in an excited state, and that would mean that there might be a gap. The outermost electrons might actually be in an outer orbital. They may have, remember the last discussion, they may have jumped out an orbital, they may have jumped up the staircase, they may have moved away if it's excited, but if you add energy to an atom and you get one electron that's excited, it goes out, what is going to happen very quickly? It moves to a higher energy level. What does the electron want to do? Okay. Go back to its lowest energy level because it wants to do as little work as possible, right? It doesn't want to be excited. It wants to be left alone. It wants to go back to stability. It wants to get the remote in its hand and chips in the other hand and just sit around and be couch potato. So the electron's trying to fall back into the lowest energy state it can get to. And if all of the other orbitals, all the other addresses are full, it can only drop back to most likely where it came from. So energy's added, it's excited, it goes out to another orbital, but it very quickly, as soon as it can, wants to drop back down. And when it does that, what does it have to do? Why did it move out? It moved out because it received additional energy. It has too much energy to stay on the couch. It moves out. Now it wants to go back to the couch. So what does it have to do?
Lose energy.
Lose energy. It has to get rid of energy. And how does it get rid of the energy? It emits light. So it falls, it emits light energy. Kind of think of it this way. It's got a certain amount of energy. It says, okay, if I emit light, boom, now I have been able to get rid of some energy. I'm going to fall back to the next level. And it's going to release the amount of energy. The same amount of energy is released that would have been required for it to move out there in the first place. So if it gets a packet of energy and it's not enough to move it to the next level, it doesn't move. But once it gets enough to make the full step, boom, it takes the step, and then quickly falls back to its original position and emits the energy equal to the amount of energy it took to move it out. It emits that energy back out in the form of light. And that amount of energy, remember, gets related to the frequency of the light, or wavelength, because those things are directly related. And therefore, a certain color gets emitted. When that color gets emitted, you can tell how much energy was lost, and you can kind of build those stair steps. You can say, okay, this is a big step, and then a little step, and a little step, and a big step, because the amount of energy that's released is related to how large that step is, how much energy it took to move it out, and then how much energy it emitted when it fell back. So we used two different methods for determining the electron configurations, right? One of them that's not in the book that I taught you, and actually I think this is what they refer to on the bottom of, where's it at? The bottom of page 122. He says that some chemistry books teach a different method to get electron configurations, and basically just says there, it's a different method, but it doesn't mean it's wrong. It's just a different way of doing it. The only other way I've seen, other than using the periodic table, is the slant diagram that I taught you. And that slant diagram was the only way I learned, and then later I learned using the periodic table. So just which one was seen as being the primary way of learning that information. So does anybody in here prefer, right now do they think they prefer the slant diagram? Using the slant diagram to figure out the electron configuration, okay? Does anybody here know that they prefer the periodic table? Okay, so there's a few people. Part of what I think it is last time, and every time I've taught this course, I usually start with a slant diagram and then show you the periodic table. In this class, because of the questions about metals, nonmetals, and why are things where they're at, you guys kind of changed the course of the discussion a little bit. And so I actually introduced you to this first. And the slant diagram, you've only seen that maybe one time. I do want to go through it one more time with the slant diagram, so you've got both tools that you can use, okay? But this new edition of the book focuses primarily on using the periodic table to come up with the electron configuration. So very, very quickly, we're going to go ahead again and write the different energy levels. And I normally just go up to about 5, because once you're up to 5, you've covered most of the periodic table. I mean, you're down in this range here. Once we get into the 6th energy level, then we start taking the F shell into account and things like that. I guess a little crazy, but the basic principles, the vast majority of electrons configurations we're going to do are going to be in probably the first 3 energy levels. First 3, maybe 4 energy levels. Okay. And remember, just for visualization, there's the S shells. You have, and it's hard to do this one because it's kind of in and out of the board, but in the P's. So there's the S orbital and the P orbitals. There's a single S orbital, P orbitals, and then we have D's and F orbitals, which I'm not going to even try to sketch out. Every one of the orbitals has the ability to hold 2 electrons. So to review then, in the S orbital, It's a single orbital. It can hold a total of 2. The p's have 3 orbitals. Each can hold 2, so it has a total of 6. D has 5 orbitals. 5 orbitals, each can carry 2, so it can hold a total of 10. And then the f orbitals have 7 for a total of 14. Okay. So that's how many can fill each one of those different orbitals, or those levels of orbitals, if you want to put it that way, in order. Now, not every energy level has every orbital. As we build from the first energy level to the 5th energy level, and when you think about how much energy we're talking about, this number is primary. There's a huge difference between a 1s1 and a 3s1 electron, where its position is. So remember, these describe the positions, or maybe sometimes I'll say the addresses. This is where those electrons are probably located. You know, this whole thing is kind of fuzzy, because unlike the Bohr model and even the Rutherford model, which said there were particular tracks, the current quantum mechanical model says that an electron could be somewhere in this shell. And it's not maybe even technically orbiting, it's kind of buzzing and vibrating, and you know, and if you heard on the video, it gets kind of weird because we start talking about probable locations, and it exists as a function of the waveform. And so like this thing that we call an electron exists and doesn't exist based upon movements in the electromagnetic field. It's almost at times when you talk to philosophers of science, it's almost as if it's not the electrons that form the fields, but it's the fields that form the electrons. It's like the fields bring something into existence, and it gets all philosophical at that point. Okay, so what is, what will be, what could be, just as we talked about on the electron and the orbitals in the Bohr model, came to that understanding that the electron could exist in one orbital or the other, but it didn't exist between. It would be one place and then release energy and instantaneously be at another place. Okay, so we've got the different energy levels. The energy level that exists, or excuse me, the orbitals that exist in the first energy level, what do we have? The first energy level only has the s orbital. Okay? It only has an s orbital. And think about it this way. As we do this slant diagram, each energy level adds one of those orbitals, one of those orbital patterns. Okay? I sometimes say orbital, but like when I say the p orbital, remember it's the p orbitals. There's 3 different shapes within the p. So let's think about the orbital levels maybe. First energy level has the s orbital. The second energy level has the s orbital and p orbitals. Has both of them. The third energy level, we're going to go ahead and add another orbital level. We're going to have s orbitals, p orbitals, and d orbitals. The fourth energy level, we're going to add the f orbitals. So we've got the s's, the p's, the d's, and the f's. And just so we have some usefulness, I'm not going to add anything else. I'm just going to go ahead and write the same thing here, just so we have something to use for the slant diagram. So these are the orbital shapes, the types of orbitals that are available in any given energy level. First, second, third, fourth, and fifth, and they build. There's not a lot of hard thinking here. It's just to know it's S, P, D, F, and each one adds a different orbital possibility. The next thing is, how many can they hold? Every s orbital can hold 2, and the way we would note that is this can hold 2. This one can, these can all hold 2, a maximum of 2. They can hold 1 less, 2 less, whatever. They can hold up to 2. 6, or the p's can hold up to 6. On the video, he mistakenly said 8, but each one can hold 6. The d's can each hold 10, and the f's can hold 14. So you can see how it adds up really quickly. You add a d orbital or d level, boom, suddenly you can hold 10 more electrons. That's why the periodic table looks the way it does, and we'll go to that method in a moment to review that as well. So counting them up, here's a total of 2. Now we're at 4, 10. Here it's 18, 28 to this point. Okay? And then on 28, we can add another 16, 18, 32. So we're up to 60. You see it adds up very quickly. Now, we also mentioned as well that the orbitals are not filled in straight order all the time. There are places in the periodic table, once we start getting a large number of electrons, that the orbitals don't fill simply in this order. It'd be much easier if it just went, you fill the S, then you fill the S and the P, then you fill the S, the P, the D, then you fill the S, the P, the D to the F. That's the common error, but that's not the way it actually happens. For reasons beyond the scope of this course, you just need to know that the way that they fill, or the order they fill, is according to the slant diagram. And all you do draw those slants. And you're going to fill according to the arrow direction from the tail to the head of each arrow in order. So as you fill across, and let's just start, let's say we're making up this electron configuration for some large atom, don't even care what it is right now. What's the order they're going to fill in? First, we're going to fill the first energy level, S shell, up to 2. Then we're going to fill the second energy level, S shell, S orbitals, S orbital can hold up to 2. Then the 2p orbital that can hold up to 6. Then the 4s orbital that can hold up to 2. Nope, sorry, mistake. 3s. The 3s2. Then the 3p6. The 4s2. And then it gets off. At the 4s2, the next one to be filled would be the 3d. And the 3d can hold up to 10. And then the 4p that can hold up to 6. And then the 5s that can hold up to 2. Okay. What would be next after the 5s? 4d. And then 5p. Okay. So you see that order. So if you were to write this out and just go straight across, at a certain point you'd be fine. The hiccup happens here between the pattern changes right there. They appear to fill in order up and through P36. And actually 3P6, you would expect 3D10, but you get 4S2. And then you'll notice that it goes back to 3, and then back to 4, and then to 5. And it's going to jump around between energy levels. And it's, again, beyond the scope of this course why that is. But just need to know that that is the order that it fills. Now you could sit down and draw a standard electron configuration all the way out to, if you wanted to put 100 electrons in it, figure it out. If you wanted to go ahead and memorize what it looked like for 100 electrons, you could do that. I would encourage you. I encourage you to use the chart or do this. But once you have a standard configuration, a ground state configuration, up to past whatever number of electrons you need to account for, then all you need to do is count it up. Let's say, for example, that I'm trying to figure out the electron configuration for magnesium. Okay? It's 12. 12, atomic number is 12, so in the neutral, it's going to be 12 electrons, and in the ground state, it's going to be 12, so I count up to 12. 1, 2, 3, 4, plus 6 is 10, 11, 12. Boom. That is my electron configuration for magnesium. Let's say I wanted to build from there. Let's say I'm not looking for magnesium. Let me take it a little bit farther. Let's say we're looking for silicon. Silicon is 14. I need to count for 2 more. Those 2 more have to be in this address here. So I've just moved over here to the 3p, but rather than 3p6, I'm just going to have 3p2 because I only need 2 more electrons. But I can take the 3p up until 6. So let's see, 2, 4, 10, 12, 18, 19. So if I were looking for potassium, I would be 4s1. So again, once you draw a standard configuration, then all you need to do is count up to whatever number you're looking for. Or if you want to do it on the fly, say, I need to, again, do magnesium for 12. Oh, that would be 2, 4, 10, 12 right there. This is my energy level, my last orbital. Going to be in the 4s2 position for magnesium. Okay, so that's using the slant diagram. And again, that's not the technique that's taught in the book. This book focuses more primarily on using the periodic table. And again, looking at the periodic table as we've done several times, so again, this is review of review for us, but we can see that the same pattern right here is lived out in the formation of the periodic table of elements. Moving from the top, the energy levels are represented by the rows that they're in. Okay? The columns represent the fill orbitals, the orbitals that are being filled. And we see here that this is the s block right here. This is the s orbitals get filled in these positions. Remember that helium over here is actually part of the s block. So for what we're doing here, doing electron configuration, remember helium should be over here for electron configuration, just as hydrogen should be over here for determining metal or non-metal. So if you view helium as being over here, and you were to start counting up using the same thing, magnesium, or excuse me, yeah, let's use magnesium again. We see it's 1s1, 1s2. And what I'm saying when I say 1s2 is what is the position of the valence electrons, the farthest electrons away from the nucleus. Helium has 2 in the s orbital. Going to the second energy level, lithium. Lithium has 1 in the 2s orbital. So 2s1, 2s2. Then after the 2s2, it goes to 2p6. We see that from going 2s1, 2s2. Oh, now we're in the p block. p1, 2, 3, 4, 5, 6. That's represented by these p6s here. The next is the 4s. We come back over here. We're in the fourth energy level. Excuse me. Third. I just did second, so we're actually not in the third. Third energy level, 3s1, magnesium, 3s2. And that's where we said before we would need to stop right here at 3s2. So whether you figure out the configuration by using a slant diagram or over here on the periodic table. Now the one trick or the one common mistake, we covered this yesterday, happens whenever we get to the d block. We get to the d orbitals. So we've got 1s, 1 and 2, 2s, 2p, 3s, 3p, and we have 4s. Potassium is 4s1, calcium is 4s2. Right? Now we go to the d block. What is the thing we have to remember when we travel into the d block? Take the energy level minus 1. So this is 4s1, 4s2. This would look like it's 4d1, but it's actually 3d1. 3d1 through 3d10, and then it goes back to 4p. So everything in here in the d block, you've got to take 1 away from the energy level. Now that makes sense when you look here because it goes from 3s, 3p, 4s, 3d. See that? You lose an energy level here, but you gain it back when you go to the p. That's if you take into account that when you come into this d block, you need to remove 1 from the energy level. Very common mistake if you use this method, that you're going to go 3s2, 3p6, 4s2, 4d10, 4p6, and you'll have your energy levels off. So again, when you're using that method, make sure when you travel through the periodic table in the d block that you subtract 1 from the energy level. Example 3.4, and I'm going to leave that standard notation up there because this is good for, you know, every electron configuration. This is a good starting point. If I had this, and I said, for example, on 3.4, it says, what is the electron configuration of carbon? So before I can do the electron configuration of carbon, what do I need to know? I need to know how many electrons carbon has, right? If I want to try to place them, I need to know how many I need to place. I look for carbon, I find that its atomic number is 6, so it has 6 protons. I'm going to assume, unless I'm told otherwise, that it's a neutral atom, meaning it's going to have 6 electrons. All I really need to do then is count up to 6. If I have this, 1, 2, 3, 4, I need 2 more. So for carbon, is going to be 1s2, 2s2, 2p2. See? There's 1, 2, 3, 4, 5, 6 electrons accounted for. And they fill in this order. I need both of those, and I only need 2 in the p level to get 6. So I stop my count up right there. If I use a slant diagram, 1s2, 2s2, 2p2. If I use the periodic table, 1s1, 1s2, 2s1 and 2, 2p1, 2p2. Okay. Next one says write the electron configuration of chlorine. Again, I'm going to say, okay, chlorine, how many electrons do I need to place? Find chlorine, it's a column 7 gas, 17. If I had this on my paper, I'd go, okay, 1, 2, 3, 4, 10, 11, 12, 13, 14, 15, 16, 17, 18. I don't need one of those. One, 2, 3, 4, 10, 12, 17. 17. I say we end at 3p5, 3p, 1, 2, 3, 4, 5. 3p5. 1, 2, 3, 4, 10, 12, plus 5 for 17. And lastly, give the electron configuration of Ag, which is silver. 47. Sir?
So would the right answer on the test be 3p5, or do you have to write it all out?
We're going to go review the shorthand in a moment. But until then, this is referred to as the full electron configuration. There's also an abbreviated, and you'll be asked to give the full or give the abbreviated. So yeah, but yeah, the answer right now, if you were to give the full electron configuration, would be to write out the whole thing. So for gold, or excuse me, for silver, 47, we need to count for 47 electrons. 1, 2, 3, 4, 10, 12, 18, 20, 30, 6, 37, 38. It's a 2, yeah. So I'm going to need to go back to 4D10, but that would give me 52, right? So 4D10 would give me 52. I need 47, so I'm 5 heavy. I need to remove 5, which makes this a 4D5. Does that make sense? Let's count it up again. 2, 4, 10, 12, 18, 20, 2, 4, 10, 12, 18, 20, 30, 36, 37, 38, 39, 40. That'd just be 40. $38. We need 9. How about that? 2, 4, 10, 12, 18, 20, 36, 38, 47. Okay?
So why would you use 40?
Well, if we look over at the slant table, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10.
Oh, okay.
4d10. I could have up to 4d10, but I don't have to fill it all. I could have up to 10, but I could use 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. I only need 9. So using the count, which comes from the slant would say I fill up to the 4d9 position. Let's see if that makes sense. Over here on the periodic table, silver at 47. I would know I'd need to count up to what? This position here is at the 5th energy level, but when I get into the D section, it becomes the 4th energy level. So it's the 4 D 1, 2, 3, 4, 5, 6, 7, 8, 9. 4D9 is my highest electron in the configuration, and that's what I have over here, 4D9. Let's go ahead and use this up here, which is the electron configuration for silver, and use this to, again, teach the abbreviated electron configuration. For the abbreviated electron configuration, what we do is we're going to refer back to the noble gases. The noble gases are those column 8 gases all the way over here on the right-hand side. Neon, argon, krypton, xenon, these over here. We're going to learn later on that those gases don't want to react with anybody. They are perfectly satisfied to be what they are forever. They don't need anybody else, okay? And so they're very, very, very stable. Because of that, we tend to use them as a reference point. And what we do for electron configurations is we find the position of whatever it is we're trying to solve for. In this case, we're using silver. And for silver, we have written out the full electron configuration. But if we look to the preceding noble gas, what is the preceding noble gas? The noble gas that was created before we got to here. That's going to be over in this column somewhere. You know, and the shortcut is I'll read across and go up 1. I'll just read to the end and go up 1. What am I saying? Well, basically I'm saying as I built my electron configuration, at some point I happened to hit a noble gas. For example, the 2p6 block here, that's the electron configuration. That full is for neon. 2p6 is neon. And then 3p6 is argon. Argon. And then 4p6 is krypton. Okay? And if we had it, we could go out to xenon if we went all the way out to 5p6. So those, when we fill to that point, we have the electron configuration for neon. Here it's argon. Here it's krypton. What we do for an abbreviated electron configuration is go to the preceding noble gas. In this case, at one point I made krypton. It was right there. That was the address. That was the full electron configuration for krypton. I have krypton plus a few more. So the way I can write this whole thing out is to say that I have krypton, put a bracket around it, the chemical symbol for it. I have krypton plus the 5s2 and the 4d9. This is the abbreviated electron configuration. What we're assuming is anybody, even your little kid brother, could figure out what the electron configuration for krypton is. So just go ahead and write krypton plus a few more. And you would say krypton plus a few more until you built all the way up across here, you know, until you were past this line, past xenon, and you came over here to cesium. And once you start another line, now I could abbreviate cesium and barium. I could abbreviate them by using krypton, or excuse me, xenon as my noble gas. So the electron configuration for barium, if you had this in front of you and you were asked, what is the electron configuration of barium using the periodic table? All I do is go to the preceding noble gas, whether you go up 1 and across or across and up 1. The preceding noble gas would be and 6s2. I'm done. If I'm looking for the electron configuration of barium, and I'm using the abbreviated electron configuration of barium, I go to the preceding noble gas and then count up from there. So it's xenon plus 6s1, 6s2. There it is. That's incredibly fast. Because if you can locate it on periodic table, go up 1 row, go all the way to right, write it down, and then build from there. Just build up the next row. Now tell me, if you had come into this classroom a week ago, maybe a week and a half ago, and you saw this on the board, what would be your emotional response to that? Okay? Now you look at it and you're going, what? Hopefully not the same, right? Hopefully it's a little bit more like, oh, okay. Oh, wow, this is really easy. Man, hope on the exam I have a periodic table and it says, write the abbreviated electron configuration for anything. It's easy. All I do is build up across, and if I remember that when I get to the D block, I subtract 1, and then when I get to the P block, I add it back, I'm good. I can do that. Because at the most, I'm going to have to count up 1, 2, plus 10, 12, plus 6, 18 electrons. At the most.